Hello all, and welcome to this new session of this course Pre-MBA Statistics. So again, just to quickly revise as to where we stand, so this entire week has been more about, let's say, random variables, more from a discrete point of view and continuous point of view. So again, if you vaguely remember, we started the week with discussing a few random variables such as binomial, Poisson, which were discrete examples, and then we slowly transitioned into something like normal distribution, which is more like a continuous distribution, etc. So just in the last session, we talked entirely about normal distribution, empirical rule, properties of normal distribution, parameters of normal distribution, etc. and so on and so forth. Now again, like I said, the whole idea of discussing random variables is what? So again, let's say if you bring in any practical data, so we should be able to fit some sort of a distribution on that practical data or on that real data. So let's say if you're bringing a practical data which is a discrete, so just to give you an example, let's say some count data where you have number of insects in a field or number of accidents in a day on a stretch of road, okay, or number of disease cases in a town. So all these could be modeled using some sort of a discrete distribution, let's say such as Poisson or its extensions, okay. And another example could be, let's say if you bring in some continuous data, let's say income data or scores in exam data, then we can sort of fit a normal distribution on top of that, okay. So again, just to summarize, the entire idea about discussing random variable is that if you bring in any real data and then ultimately where we are sort of heading now, right? So we are sort of heading towards estimation or inference, and inference and estimation about what? So inference about the unknown parameters in the distribution. So let's say if you bring in a practical data and then you assume that a normal distribution is a good fit for the real data, then what exactly are the parameters under a normal distribution? Again, two parameters, so mu and sigma square, which are nothing but the mean and variance of a normal distribution. So assuming that both these parameters are unknown, then how do you sort of estimate those, and then how do you sort of apply the estimators of the parameters to sort of solve slightly advanced problems such as confidence intervals, testing of hypotheses, etc. Okay. So currently we are right at the stage where sort of we have explored all throughout this week about random variables, like I said. And now particularly this session would be again a small practical session. So we'll see several examples and then several examples pertaining to, let's say, binomial distribution, Poisson distribution, normal distribution, and what sort of questions could be answered pertaining to all these distributions and how those questions could be answered. Okay. So again, as the name suggests, so some practical examples using case studies. So we'll take up some inbuilt data sets maybe in R or some other software, and again don't worry. So I'll tell you exactly as to how do you access the data sets, or maybe I'll give you a copy of the data set so that you can sort of download the data sets and work on your own. But again, the idea is that whatever distribution we study in the last session, we'll sort of try to implement those distributions on some practical data sets, okay, and hence the name practical examples using few case studies. Okay, so we'll start with a very famous first data set, and then this data set will throw some light upon the binomial example, or rather the binomial distribution. So again, what exactly is the data set? Very briefly, I'll explain the data set first. So this data set contains student admission records at UC Berkeley in the US. Okay, so student admission records at UC Berkeley in the US. So the data set contains aggregate admissions, and rather aggregate admissions record of graduate school applicants at UC Berkeley for the 6 largest departments in 1973. Somewhat an old data set, but again regardless what exactly the data set contains. So again, like I said, it contains some aggregate of admission records of graduate school applicants at UC Berkeley for the 6 largest departments in 1973, classified by admission and gender. So again, if you see a snapshot in the next slide, I'll show you a snapshot of the data set. So you will kind of get to know that the data set contains these 3 variables. So the first one is admit. Admit stands for what? So whether the student is admitted or rejected from the school. Second one is gender, so male or female. And again, like I said, it pertains to 6 largest departments. So department, I have simply named them as A, B, C, D, E, F. Okay. So relatively small data set, but again, we'll try to sort of find out that what sort of binomial distribution could be fitted on the data set, on what variable. And once you fit a binomial distribution on some variable, then what sort of questions could be answered in a later stage. Okay. Okay. So again, like I said, this is just a snapshot of the entire student admission in UC Berkeley data set, and again this is just a first few rows of the data set. Again, like I said, you have more number of rows in the entire data set. But again, like I said, you only have 3 important variables here. So the first one is admit, and you can clearly see that admitted or rejected pertaining to a student, then of course gender, then department, and now the last column gives you frequency. So again, frequency we studied a lot of times in the first week itself. So what do you mean by frequency? So let's say 512. So in the entire data set you have 512 students who are admitted having a gender of male from department A. Okay. Similarly, if you look at this number, which is 8, relatively low, which is the number of rejected applicants who are females from department B, and so on. Okay. So this is exactly how you should read the data set. So once you get a hang of how should you read a data set, then sort of answering any questions which follow are slightly easier. Okay. So again, just to repeat, student admission at UC Berkeley containing only 3 important variables: admit, gender, and department. And then the last column gives you the frequency, which means the number of students falling in that category. Okay. Okay, so again we'll see, or rather we'll try to see some questions which could be answered using the UC Berkeley dataset. So the first one is probability of a person being admitted. So kind of a simple question. So what exactly is the probability that a person coming to UC Berkeley in any of the departments, regardless of the departments, what is the probability of a person being admitted into the school? Okay. So again, what exactly is the summary here? So find out the probability that a randomly chosen applicant is admitted. So again, the question is kind of easy, like I said. So you have to find out the probability that if you pick a random person or random applicant, so what is the probability that the random applicant is admitted into the UC Berkeley school? So again, you may pause the video and then you may gauge on whatever been taught all this while and try to understand that how should you answer, or how should you at least go forward to answer this question. Okay, so as simple as that. So what we have to compute is you have to compute a probability measure, which is P, and then how do you get that probability? So you want to find out the probability of a random person being admitted into the UC Berkeley school. So you look at the total number of applicants being admitted and simply divide by the total applicants that you have in the entire pool, isn't it? So again, if you go back a slide, if you vaguely remember, the first column gave you admit criteria. So some of the students are admitted in the school, some of them are rejected from the school. Okay, so not all the students are admitted in UC Berkeley, of course. So we have to find out that if a new person comes, what exactly is the chance that he or she will be admitted to the school at UC Berkeley. Okay. So as simple as that, we can get a data of all the students who are admitted in the school divided by all the applicants in that season. Okay. Alright, so again, if you gaze through the data or if you run through the data, you will find out that answer to this question is kind of easy. So these are the number of students who are admitted, 1755. And these are the total number of applicants. So if you take the ratio, so 1755 divided by 4526, the answer comes out to be 0.3877, which is roughly 39%. Alright. So relatively 39% is a much lower sort of a probability, which is much lower than even half. So not even half of the students who apply to UC Berkeley, regardless of the departments, get actually admitted in the school. Okay. But again, try to understand that how are you sort of finding out the answer to the question. So some of the questions you need not go into, let's say, any distributions as such. So look at the data, find out the total admitted applicants, find out the total number of applicants in the pool, simply take the ratio and find out the probability. Okay, so again continuing from the same spirit, so again the same questions of probability of a person being admitted, and again we talked about the summary of the problems. You have to find out the probability that a randomly chosen applicant is admitted. Now exactly how do you interpret the probability? So again, if you remember, the probability was 0.39 roughly, so 39%. So how do you interpret this number 39%? So 39% is nothing but the probability that a randomly chosen person is admitted, which is, like I said, which is much lower than 0.5, indicating the tough entry process into UC Berkeley. Okay. So once, if somebody gives you a probability value, you should be able to sort of interpret the probability. I mean, what do you mean by that probability number? Okay. If the probability is less than 1/2, then what do you mean by that? If probability is more than 1/2, then it sort of points to a certain idea, a certain conclusion, etc. So again, interpreting the probability is also important and not just writing down the number. Okay, so again slightly deviating from the first problem, now the entire same data as such, which is again the UC Berkeley admissions records data. And now the second problem is that male applicants to department A. Now this is somewhat specialized sort of a question that we are asking, that we are focusing only on the male applicants firstly, and only on male applicants who are admitted to department A only. So again, if you remember, you had 6 departments, A, B, C, D, E, F, right? And then we want to focus on male applicants to only department A here. Now again, if you go back and then you have a look at the data, then let n be the total male applicants to department A and let x be the number of these admitted. Okay. So what exactly is n again? So n is nothing but the sample size of total male applicants to department A, and x is nothing but the number of these admitted. So again, if you run through the entire data set, you will find out that from the data your n is exactly 825 and x happens to be 512. Now again, once you get hold of these two numbers, finding probability is kind of very easy now. So you simply take the ratio. Thus, the estimated probability of a male applicant to department A is nothing but the ratio of these two numbers, which is 512 divided by 825, which is 0.62. So again, 0.62 is relatively higher than 0.5, which means that if an applicant is male, then probability that that applicant who is a male applicant gets admitted to department A is higher than 1/2. Okay. So again, why are we comparing all these values with 1/2? Because 1/2 is more like randomized probability, right? I mean, the person is either admitted or not admitted. Okay. So if a person is actually admitted to department A and he is a male applicant, then the probability happens to be 0.62, which is higher than 0.5. And then how do you interpret this number? So again, interpretation is kind of easy, that since 0.62 is slightly more than 0.5, then it's kind of higher. So you have higher probability that a male applicant gets admitted to department A. Okay, now more importantly, how do you bring in the idea of a binomial distribution here? So again, I'll try to explain this very briefly. Now assume that x follows a binomial NP distribution. Now again, what do you mean by x here? So again, x stands for, so x is a random variable and x stands for the number of male applicants to department A. Okay. So again, remember, we assume that x is a random variable, which is nothing but number of male applicants to department A, of course, who are admitted to department A. Now assuming that x follows a binomial NP distribution, again you may pause the video, you can go back to the previous video where we discussed binomial, its properties and so on. I mean, how do you design a binomial distribution, what do you mean by the parameters of a binomial distribution, etc. But assuming that x follows a binomial NP distribution, we have to actually find out the PMF at the observed value of x, which is 512. So again, assuming, so what we are trying to achieve here, we are trying to achieve that if you assume a certain binomial distribution on the random variable x, which is n comma p, then finding probabilities is equivalent to finding PMF at that value. Okay. So when we say that we have to actually find out PMF at that value, what are we trying to achieve here? We are trying to find out probability that x equals 512. Okay. So essentially we want to find out that what is actually the probability that there will be 512 male applicants who are admitted to department A out of all the overall applicants. Make sense somewhat? So we are trying to find out this probability, and then if you assume a binomial distribution, finding any probabilities comes from the PMF. We have actually discussed this part in some of the earlier sessions. Okay. Now this is nothing but the binomial PMF. So simply write down the binomial PMF. You know the value of n is 825 and my P happens to be nothing but 0.62. Now again, why 0.62? Again, if you go back a slide, then I am kind of borrowing the probability from the previous question, which is 0.62. Okay. So my n happens to be 825, my x value happens to be 512 and my probability happens to be 0.62. So essentially what we are trying to find out is that if the number of male applicants admitted to department A at UC Berkeley follows a binomial NP distribution, then what is the probability that you are actually observing the value of 512. Okay. And then you can plug in all the values in the PMF. So 825, choose 512, and then p to the power 512, so 0.62 raised to the power 512 into 1 minus p, which is 0.38, into 1 minus p, which is 0.38 raised to the power n minus x, which is 313. And finally, interestingly, the answer comes out to be very small, which is 0.0286, which is roughly about 2.86%. Okay. So assuming n is 825, what is the probability that you are actually observing 512 male applicants to department A? Probability is relatively very small there. Okay, so now what? So let's say if you extend the size of n, or rather if you extend the value of n, okay, then how do the probability change? So now I am kind of bringing a slight extension to the same problem. So again, the problem is what? So male applicants to department A. Now again, assuming that x follows a binomial NP distribution. Now again, let's say in the next year you have a future batch of size 1000. Okay. So let's say next year you have a future batch of size 1000, then what is the probability that there will be at least 600 male applicants to department A? Okay, so what is the probability that in a future batch of size 1000 there will be at least 600 male applicants to department A? So again, how do things change? Again, assuming that you have a binomial NP distribution to X, now my N happens to be 1000, my P can be borrowed from the last slide, which is 0.62. And now since you want to find out that what is the probability that at least 600 male applicants are admitted to department A, we are trying to find out this probability, that probability that X exceeds or rather is bigger than equal to 600. So what do you mean by this? So we can borrow the binomial PMF, so Px, and you have to actually sum all the values from 600 all the way up to 1000. Okay, so I can actually do this entire thing in a software, and then the final probability happens to be 0.9088. So how do you interpret this? So we have roughly 90% chance that in a future batch of size 1000 there will be at least 600 male applicants to department A. Okay, so now if you change the thing slightly, so now the focus is what? Now the focus in the third problem is female applicants to department C. Alright, so female applicants to department C. Now again, all the things are kind of they stay the same. It's just that we are focusing now from a male applicants to female applicants pool, and again to department C. Okay, so again the same thing. So let N be the total female applicants to department C. Let X be the number of these admitted, as we did earlier. So from the data we can actually find out that N happens to be 593 and X happens to be 202. Thus the estimated probability of female applicant to department C is simply the ratio. So 202 divided by 593, which is 0.34, so 34%. Okay. So again, if you go back a problem where we had male applicants to department A, there the probability happened to be 0.62. Okay, and similarly here in this third problem, the female applicants to department C, the probability happens to be 0.34, which is relatively low, even lower than half, one half, right? Which means that there is not much chance that if an applicant is a female applicant, she will be admitted to department C. Okay. But now similarly we can sort of play around with this data that we have. Now again assume that X, which is a random variable, follows a binomial NP distribution. Then now the things are slightly different, the problem is slightly different. So you have to find out the average number of female applicants to department C in a future batch of size 1000. Okay. So how do you attack this problem? So finding the average number of female applicants in a future batch of size 1000 which are admitted to department C. So again remember, if you have a binomial NP distribution, what exactly is the mean formula? So the expectation formula of a binomial random variable is nothing but N into P, and N in this case is 1000 and probability is 0.34. So the average number of female applicants to department C admitted in a future batch of size 1000 is nothing but 340. Okay. So once you sort of fixate a binomial distribution and its parameters, so answering any follow-up questions are kind of easier. Okay. So once you know what is N, once you know what is P, then answering any probability questions, answering average questions, variance questions, they sort of are much more clearer. Okay, so now similarly, exact same problem. So female applicants to department C. Now find the variance of the number of female applicants to department C in a future batch of size 1000. So in the earlier side, we found out the mean or the expected value, and now here we'll try to find out the variance in a future batch of size 1000. So again, you simply plug in the variance formula, which is NP into 1 minus P. N is 1000, P is 0.34. So 1 minus P happens to be 0.66. So the variance here happens to be 224.4. Okay. So again remember one thing, that if you are assuming a binomial distribution, then you should sort of remember these two things. So mean is NP and variance is nothing but NP into 1 minus P. So this guy is E of X, which is NP, and then this guy is variance of X, which is NP into 1 minus P. Alright, so slightly different example now. So we are done with dataset 1. Now dataset 2 pertains to a Poisson distribution example. So how do things change? What can we sort of try to answer here? We'll see. Okay. Now just like we did earlier, so we'll try to explain what exactly is the data here. So dataset pertains to number of breaks in yarn during weaving. Okay, so number of breaks in yarn during weaving. Now again, the very first instance you should remember that if you're seeing a data set which is giving number of something, so number of something, like I said earlier, means nothing but count data. Okay, and one possible distribution to model any count data is a Poisson distribution. So we'll do exactly that. Okay. So now a brief description of the data set. So what exactly the data set means? So the data set gives the number of warp breaks per loom where a loom contains a fixed length of yarn. Again, the data set gives the number of warp breaks per loom where a loom contains a fixed length of yarn, And all these are the variables. So breaks, wool and tension. So what do you mean by breaks? So number of breaks, of course. Wool means what? So type of wool, so either type A or type B, and tension stands for the level of tension, so either low, medium or high. Okay. So again, in the entire data set, I'll show you the snapshot of the data set in the next slide, but the entire data set sort of revolves around these three major variables. So breaks, wool and tension. So number of breaks, type of wool either A or B, and level of tension either low, medium or high. Now again, as before, this is a snapshot of the data set. Again, of course, it contains many more rows here. So I am only showing you the initial 10 rows. So again, remember what exactly is the data? So number of breaks in yarn during weaving. So how many breaks are you seeing in the yarn while you sort of do some weaving there? Okay. So the first column gives you directly the number of breaks, then the type of wool, so either A or B, and then tension. So again, if you remember, tension has 3 levels, so low, medium, high, and type of wool has 2 levels, so type A and type B. Now again, what sort of questions could be answered from a Poisson example? So again, remember that assuming that x follows a Poisson distribution here. So again, what is x here? X is a random variable, and here we are defining x to be nothing but the number of breaks. Okay, number of breaks in yarn. So again, number of breaks means some sort of a count data, and count data, like I said earlier, could be modeled using a Poisson distribution, but not a binomial distribution. Okay, so the entire idea or the entire experiment is different here. Anyways, but then if you define x to be a random variable, which is the number of breaks in yarn, then let's say that you are assuming x to be a Poisson distribution with parameter lambda. So any Poisson distribution is sort of depends on a parameter lambda. And now the question is that find out the value of lambda simply. Okay, so how do you find out the value of lambda? So again, if you go back to the Poisson session where we discussed properties of a Poisson distribution, from there you will understand that lambda is nothing but the sample mean. Okay, because lambda is nothing but the average of the number of breaks in the yarn. Okay, so simply look at the entire data, look at the breaks column, and simply find out the average of all the breaks, which is nothing but the sample mean, and answer comes out to be 28.14. Okay, and as part of estimation, what we do, so if you look at the data set and if you see that the average number of breaks happens to be 28.14, then as a next step we can sort of propose that that number 28.14 can be directly linked to the unknown population average, which is lambda here. Okay. So finding out the value of lambda means what? If you understand that for a Poisson distribution lambda stands for the population average, then take the entire data of number of breaks from the last slide or from the entire data set, find out simply the average of number of breaks, which is 28.14. And lastly, you simply sort of conclude that 28.14 is a good estimate of my unknown population average. Alright, so just in an instance, I have sort of drawn several Poisson PMFs. So this graph is sort of just to explain that how do each and every Poisson PMF looks like for varying values of lambda from 20 to 35. And here you will see that I am fixing lambda values all the way from 20 to 35. So each color or rather each curve here depicts a particular lambda, or rather a Poisson PMF or a Poisson density curve or a Poisson PMF curve for a particular lambda. Okay. So just to give you an example, if let's say lambda is 20, which is the very first curve in red that you see here. So again, like I said, lambda is nothing but the mean, isn't it? So lambda is nothing but the average. So can you see that for the red curve, the average sort of falls around 20 here. So average means the midpoint, isn't it? So average has to be around 20 here, and then it's kind of symmetric around the average. And as and how you will change lambda, so again the very last instance is what? So lambda is 35. So as and how you will shift from 20 to 35, the curves are also shifting from, let's say, the average being 20 to 35. So again, if you see here, the average pertains to roughly around 35 there. So I guess this slide is more important to tell you the behavior of a Poisson curve or a Poisson PMF curve depending on what value lambda takes, kind of. Alright, so the second part of the same yarn data is finding some probabilities. So can we actually find some probabilities now? So assuming that x follows a Poisson 28.14, and how do you get this value? From the first part of the same problem. So assuming that the random variable x follows a Poisson distribution with lambda 28.14, now you have to actually find out the probability that x equals 20. Okay, and how can you do it? So you look at the PMF of Poisson distribution, this is the PMF, and simply plug in the value of x to be 20 and lambda to be 28.14 and then evaluate. So finally the answer comes out to be 0.0238. Okay, so assuming that x follows a Poisson distribution with lambda being 28.14, probability that x takes a value 20 is very small. So, 2.38% only. Okay, so how about such a probability? For the exact same problem, if you want to find out probability that x is less than equal to 40, then again look at the Poisson PMF, and then here you have to actually sum all the PMF values from 0 all the way up to 40, okay, because this is nothing but some sort of a CDF calculation that we are performing, okay. And now the answer comes out to be 0.9865. So the cumulative probability up to the point 40 happens to be 0.9865. Now lastly, let's say the next problem is dealing with comparing mean breaks. So again, if you remember from the data set, how many wool types do you have? So you have two wool types, isn't it? So A and B. So compare mean breaks for wool types A and B. So can you compare the mean breaks for the two wool types? So firstly, how do you want to sort of attack the problem? So the very first thing you can do is simply find out the average number of breaks within each wool type. So x bar of wool type A is 31.03, x bar of wool type B is 25.25. And how do you interpret the averages now? So hence, on an average, there are more breaks in type A as compared to type B. So if you have two wool types A and B and the averages happen to be 31.03 and 25.25, then on an average there are more breaks in type A than compared to type B. And lastly, we can sort of create box plots. So comparison of breaks by wool type. So the first box pertains to wool type A on the left side. The second box pertains to wool type B. And the idea behind box plot is what? You can see some outliers here in wool type A, right? And by the way, what do the data suggest? So data contains nothing but number of breaks pertaining to each of the wool type. So again, clearly from the box plots, you can see that the median, so this horizontal line in between the box stands for the median. So the median number of breaks in wool type A is again slightly higher than the median number of breaks in wool type B. And overall, the overall spread of the number of breaks in wool type A is much higher than the number of breaks in wool type B. Okay, so how do you gauge on the spread? So spread means nothing but the entire span of the box from the lower end point to the upper end point. Okay. So again, understanding or rather concluding a few points from the box plot or any other plot, you should be sort of be able to do that. Okay, so if you're given with the data, if you want to compare, let's say two steps or two populations, two samples, then how do you compare based on box plots, histograms, etc. Okay, so through all these examples, the idea was just that how can you sort of apply distribution to a couple of real data sets? How can you sort of answer a few questions pertaining to binomial, Poisson, etc. And then in the next session or rather next week, we'll talk more about, let's say, estimation. So once you sort of have a very basic idea about how do you approach the EDA, so exploratory data analysis, then the immediate next step would be estimation, inference, hypothesis testing, modeling, etc. Okay. Thank you.